Dr. Singh, you are in a team.
Yes, yes, yes.
Right now we have a break.
Okay. Are you getting my voice?
Yes.
Okay. Just I'm checking my system. Now it is working. No
Are you
problem.
familiar to share your PPT? How to share it?
Yes, yes, I am sharing. Just wait.
Dr. C, little bit fast.
Yes, yes. Just wait.
We have next session at 1:30.
Okay. Just wait.
Just beside the leave button, there is a up arrow button with a up arrow. You just need to click.
Uh, Up arrow. I'm not getting the up arrow option here. That is the problem. Uh,
Near the leave button.
okay. Please give me the access of sharing. I think I'm not getting access of sharing
Yes, right now you are not
from
at
your side.
presenter, that's why.
Okay.
So when your session will come, we'll do that.
Okay. Then how to share my PPT? Can I mail you?
No, 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 no. Just
No.
you need to open in your computer and you need
Okay.
to share your PPT.
Okay. 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 Okay.
You can share your screen also.
Okay. That means at this moment I don't need to share anything, huh?
Nothing, nothing. Okay.
Yes. Yes. Okay. Okay, sir. No problem.
Good afternoon, madam.
Good afternoon.
Thank you. Thank you for joining us. We'll start at 1:30.
Yes, sure. Yeah.
Are you familiar with Microsoft Teams, madam?
Yes, we use Microsoft Teams also.
Okay.
So, yeah.
So now you are presenter. So if you want, then you can share your
Yeah,
screen.
yeah, I can do that.
Yes, it is visible.
It's visible. Okay.
We'll wait for 4 minutes.
Do you want me to switch on my video?
Yes, if possible, then it's good for us.
Yeah.
Thank you. Yes, madam. Shall we start?
Yes.
Good afternoon, one and all. I welcome you all to this third international conference on soft computing and engineering applications, icSoftComp 2021. The theme of the conference is soft computing for smart nations. This conference is technically sponsored by Springer USA, financially sponsored, co-sponsored by Charotar University of Science and Technology and Department of Science and Technology, Government of India, and GUJCOS, Gujarat Council of Science and Technology. Due to this pandemic situation, we are organizing this conference on a cyberspace virtually. like as we know that there are three pillars of this and neurocomputing. And in these three main areas of software computing, we have received around 247 papers from the researchers of more than 15 countries. And the different kinds of paper like work in progress paper, main large paper, and then short papers that we have received. And we follow the double blind peer review process, and we have around 200 US institutes. And after following this review process, we have accepted around, not around, we have accepted 33 research paper for Spinger track, and all these selected papers and presented papers will be included in the Spinger CCIS as a proceeding. So, like acceptance rate is like less than 15 percentage for that. And this conference mainly comprise of keynote speech. Then we have invited talks. Then we have tutorial and around 10 technical sessions that we have in this conference. We are uh, grateful that our management of this Charotar University of Science and Technology has given us this opportunity to organize this conference, and also like sponsor finance also. I'm also thankful to our Dean and Principal, Dr. Atul Patel, for believing in me and giving me this opportunity to organize this conference. Since last 3 years, we are organizing this conference. We are really grateful to the management of this Charotar University of Science and Technology. So, other thing is like for this inaugural session, as a keynote speaker, we have Dr. Susila Devi. She is a principal research scientist at the Department of Computer Science and Automation, Indian Institute of Science, Bangalore. And her research interests are mainly this pattern analysis and machine intelligence. And she is also associated with this PAMI lab, that is a pattern analysis and machine intelligence lab of IIS Bangalore. Her other research area interests are data mining, soft computing, social networks, and deep learning. We are really grateful that we have Dr. Susila Devi as a keynote speech for this icSoftComp. I formally welcome you, madam, on this icSoftComp conference, and I hand over this to you to deliver your keynote speech. Thank you, madam.
Okay, so I'm going to be mainly talking on use of soft computing for some machine learning problems. So there are a whole lot of applications of soft computing, but I'm actually concentrating on the machine learning problems. So I'll just give a few examples of that. But before that, just I'll go into what is soft computing. I know that a lot of people are already talked about soft computing, etc. But I'd like to just have a very short introduction on that. So basically, soft computing are a set of techniques, not just one technique, and they have a certain number of different characteristics which they follow. So, first of all, it's a system which sort of adapts itself to solve the problem. So, it keeps searching for the problem. So, that is one aspect. Another is that it uses some sort of a feedback. And a third aspect is that it mimics the behavior of some animals like ants, fish, etc. Right? And you have two types. For example, when we say soft computing, it means that it's a contrast to the hard computing which we talk about. So hard computing is what we generally use. So that is the deterministic type of calculations. So whenever we learn algorithms in data structures and algorithms, etc., we use mainly the hard computing aspect. And in hard computing, we have fixed algorithms which give you the result. Okay, and the result which you get is 100% accurate. But in soft computing, what you're doing is that you're tolerant of imprecision, uncertainty, a partial truth, approximation, etc. So the idea is that one thing is that there may be uncertainty in the data which you're getting. So when you have that uncertainty, how do you deal with it? Second is that obviously there is imprecision in the calculation, and as you keep going through the algorithm, maybe you're getting something in between which is not the complete truth but the partial truth, right? And we use some type of approximation here, and even the final solution which you get, okay, you're not like you, it may not be the exact solution, but it is sort of very close to your exact solution. So it mimics human reasoning, etc., right? So here we have some differences between hard and soft computing: precision, certainty, etc., for hard computing, right? And this uses unconventional computing, and the role model is the human mind, etc. Method of search and solution is close to the exact solution, right? But may not be the exact solution, etc. Okay, so you have imprecision, some type of learning taking place. You have uncertainty, optimization in the evolutionary algorithms. So you have unconventional type of optimization, which is done over here. So what you find is that over time, soft computing has become very popular, and there are a number of, research papers which are published, etc. in that, right? So what you find is that the models may be like, for example, if you take fuzzy systems, etc., you can have linguistic models, okay, and you have some simple models which are comprehensible, etc., right? So these are the different techniques, okay, which are there in soft computing. For example, neural network, fuzzy systems, evolutionary computation. The last two are examples of swarm intelligence, okay, probabilistic reasoning, etc. So basically, what I will do is that I will take up some machine learning algorithms and show you how it can be done using any of these techniques, basically. So when we come to machine learning, what are the machine learning tasks that we are going to be talking about, basically? Okay, so basically the basic thing in machine learning is we have patterns, right? And the patterns are made up of a number of features, each pattern, and the features take a certain set of values, right? And depending on those value, it is assigned to different classes. So that's the basic idea in machine learning. There are three types of learning, which I have written here, okay? So we'll just see what the first two are. So the supervised learning is the classification or the regression task, right? So here you have a training data set available to you where you know the class label of the patterns. And when you get a new pattern, you need to find the class label with the information that is already available to you. And there are a whole number of classification algorithms that we have, like SVMs, decision trees. Okay, so neural networks, all these things are used basically. Okay, the number of techniques are there. So the unsupervised learning is the clustering which we do. Okay, so there is no class labels given to you, but you have set of patterns given, and depending on the underlying patterns in the data, you're going to put them into groups, and each group is a cluster, right? So generally what you find is points in the same cluster are similar to each other. Points in different clusters are dissimilar to each other. In other words, points in the same cluster are close to each other, and points in different clusters are far away from each other, basically. So this is the basic thing. I don't want to go into details because this is just a sort of overview, right? There is only half an hour to go through this. So let us take fuzzy set. So I will go through what is a fuzzy set very simply, and then give you 2 3 examples of how you work out machine learning algorithms using fuzzy sets. So in fuzzy sets, basically, if you have a set A, it will have a number of items, and each item will belong to it with a membership function which varies between 0 and 1, right? If this membership by a score is 0, it means that it definitely does not belong to set A, and if it is 1, it means it definitely belongs to set A. And you can have values between 0 and 1, right? So you can have 0.7, 0.6, or anything like that, right? So if you consider a set of tall people, right? So if we say that a person who's 6 feet tall will be a member of A with a membership of 1, right? But a person who is 5 feet tall, right, we can say that he definitely has a membership of only 0 to this, right? But if you have something in between, for example, 5 feet 9 inches, he may belong to A with a membership value of say zero point 0.6 or zero point 0.7, etc. So you can have any value between 0 and 1, right? So here you have the different membership values, tall and short men, right, etc. So you find that according to the height, you may find the membership value. So here, this is very small, small, medium, etc. Right? So these are just some examples. So now coming to classification, right? Let us see how we carry out classification using fuzzy systems. Okay, so here the idea is that the classes are fuzzy sets. Okay, so a class will consist of all the patterns in the set will have different membership functions. So if I have a pattern I, okay, you have a membership function mu IC, that is the it's a membership value of pattern I in class C, right? So what you do basically is when you have a pattern I, okay, you're going to find mu IC for all the classes. Okay, so once you do that, you find the membership function, membership value, which is the highest among all these, and you say that the pattern belongs to that class. So that's how the fuzzy classification is carried out. Okay, so this is appropriate where patterns do not fall into discrete classes, right? So a pattern can, belong to either one class or the other class, or it can belong to more than one class, right? So you have the multi-label classification where you have patterns which belong to more than one class, and it's appropriate for data where there is some type of ambiguity. Okay, so then you can use this type of a classification. Okay. You can also have attributes which are fuzzy, etc. Okay, so I'm coming to what is called the fuzzy KNN algorithm, right? So here you have a set of patterns, right, in your training data, and you know the class labels of all these patterns in your training data. Now you have a new pattern P, okay, which you need to classify. So what do? You find the K neighbors of P, right? Let's say K is 5. So you're finding 5 neighbors of P, right? So if we take 5 neighbors of P, right? So what you're saying is if pattern Xi, uh, if you take each of these closest patterns, right, and if you find that pattern Xi belongs to class J, then you're going to set that membership value as 1. Otherwise, all the other values are going to be set to 0. Okay. So in other words, you're going to have only 5 of these patterns having membership value of 1. So if we take this value over here, right, you're taking the distance of these, if you take these 5 patterns, only those patterns, so here we are finding the membership value of P to class I. Okay, so only those out of those k values where the membership value is 1, okay, which means that the pattern belongs to actually belongs to that class. So only those will come on the top, and at the bottom you have all the patterns. Okay, so if we take an example like this. Okay, so we have a pattern P, and these are the 5 closest patterns, and these are the distances, right? So what you're doing is, since none of them belong to class 1, okay, so you find none of these belong to class 1. So your mu 1p will be equal to 0, and mu 2p if we take, okay, you find that this second one and fourth one belong to class 2. Therefore only those two will have a mu ij of 1, right? So you are going to get only those two distances taken here, and then you have all the other distances at the bottom. And similarly, you calculate mu 3p, right? And whichever is the largest, you're going to say that pattern P belongs to that class. So this is what is called the fuzzy KNN algorithm. So let us see what do we do in the case of fuzzy clustering. So here again, we have the values mu ij. Okay, so mu ij is um, the membership value of pattern xi to cluster cj. Okay, so we have k cluster c1 to ck. So mu ij will be the membership value of pattern xi to cluster cj. Okay, so you will get some values between 0 and 1, and what you will find that every pattern will have some membership value to all the clusters which are there. Okay, and here these are the conditions. So all membership values for a pattern should sum to 1. Okay, so that is what is given here as one condition. Another condition is that every cluster should have at least one pattern in it. Okay, so this is your second condition which you have. Okay, so okay. So how do we do fuzzy C-means algorithm? Okay, so the fuzzy C-means algorithm is variation on the K-means algorithm. So what do we do in the K-means algorithm? We start off with saying that every pattern belongs to different clusters. So we set up a number of clusters at random, right? And we say assign these patterns to these clusters. And we find the new centroids, and we again assign the patterns, etc., till you find that there's no change. Okay, so the cluster centers remain the same, and you're going to stop at that point. So here what you're going to do is, there you're using the sum of squared error, which is the distance between xi and cj, right? So you're taking every point xi and the distance of that to the cluster to which it belongs, right? And you're squaring that, and you have to minimize this, right? So you want to minimize the sum of squared error. So that's the idea here. So what you're doing is you're going to choose an initial partition. In other words, you're going to take random values for mu ij, right? And using those random values of mu ij, so in other words, for every pattern xi, at random you're choosing a membership value for cluster J, right? Then you compute the centroid of each of the clusters and recompute the fuzzy partition. So that is done in this way. So this is the way you find the centroid. So usually the centroid is found by taking the values and divide it by the number, right? So here you are using the membership values also here, okay, to find the centroids. And updating the partition is done in this way. So once you do this, you are finding the new mu ij values by using this um, equation. Okay, so that's the thing. So you are taking the distance of xi from cj and you're doing 1 by that. Okay, so the idea is that the further it is, the smaller the membership function. And then you're dividing it by this normalizing factor, okay, where you're doing this for every class, okay, and you're going to divide it this by this to get some value between 0 and 1 basically. Okay, so this is the way this is done. And then we have the value of P, right? So value of P gives you how much pacification you're using over here, right? So if you find that your setting P is equal to 2, right? So you'll get this type of a thing, okay? And P can vary between 1 and infinity, okay? So as P approaches infinity, your mu ij is going to tend to 1 by k, okay? So that is something like dividing it by the total number of patterns that you have, okay? And as P goes to 1, the mu ij will tend to 1, which is like the hard clustering which we have. So the higher the value of P, more is the falsification that you're going to get over here. Okay. So this is what we mean by the fuzzy set. So suppose I have two clusters F1 and F2, right? So each of these clusters will have all the patterns that you have. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, all the patterns are there, but the membership value will change. Okay, so here the pattern 1 has a membership value of 0.9 when it comes to the cluster F1, but when it comes to cluster F2, it has a membership value of 0, right? So this is the difference. So this is how you have to describe the cluster over here, basically, in the case of fuzzy. Okay. Okay. Now I'll talk about the rough clustering. Okay. So in rough clustering, what you're basically doing is that you're saying that um, it's something like a cluster X has two types of values. So lower approximation and upper approximation. So the lower approximation consists of patterns which definitely belong to this cluster, and upper approximation those which don't, which do may or may not belong to the cluster, right? So you are going to use that formulation, and you are going to find the distance of the. So you are going to start off with a random. Assignment, and you're going to find this distance of the point from each of the clusters, and if you find that it's close enough to two clusters, then you're going to put it in the upper approximation of both those clusters, or you put it in the lower approximation of only one cluster, right? And you're going to keep doing this in a iterative way. So it is something like this. If we have three overlapping clusters in this way, you have a lower and an upper approximation for each of these clusters, basically. Okay, so these are some work which we have done. So we have done something on time series classification, where we are going to get a score, okay, and this score is the membership value, and it depends on how far that point is from the mean of each of the classes, right? And from the minimum and maximum values of each of the classes from the training data. So I don't want to go into details because we don't have time here. So let me come to neural networks basically. Okay, so I'm not also going to go into all these, but so here we have a neural network with the input and the output. Okay, so this is called a perceptron because you don't have any hidden layers in between. Okay, so what you do is you're going to give in the patterns here as the input, and whatever you're going to get output will give you the class label of your pattern. And this is the one with the hidden layer basically. Okay, so you have different types. So here we have, for example, digit recognition. If you have say 0 to 9, so you're taking this as the pixel information, and you're going to take each of these rows and you're going to concatenate it together to form your pattern, right? So you're getting 16 input values, and the output is the class label 0 to 9, right? So you could have it like either 9 outputs, or sorry, 10 outputs, 0 to 9, or you could have 4 outputs where you have four bits which give you the binary class label as the output. So here we have a neuro-fuzzy system where you're using neural networks to find your rules in the fuzzy system. Okay, so that is the neuro-fuzzy systems. I'm not going to all these because we really don't have time for that. So now coming to genetic algorithms, right? I'm not going to go into genetic algorithms, but what I want to do basically is see how you use it for clustering. Okay, so here we have a string with as many elements as number of patterns that you have. Okay, so if you have say n patterns, you'll have n elements in your string, and each of them will take a value from 1 to c, where c is the class label. So suppose we have 3 clusters, right? So we have cluster 1, 2, and 3. So we are saying element 1 belongs to cluster 1, element 2 belongs to cluster 3, etc. Right? So this is your string. And in the genetic algorithm, we have a population of such strings. Okay? And we need to evaluate each of these. So how do we evaluate it? We use the sum of squared error, basically, right? So you're going to take the sum of squared error, and that will give you your fitness value. Okay, and we have an variation of that called the. So once you do this for a number of iterations, you see the one which gives you the best fitness value, right? And that will be the pattern which you are going to basically choose. And in genetic algorithm, you in between you do one pass of k-means algorithm, right? So that is the genetic k-means algorithm. In feature selection, each element in the string pertains to a feature, right? So then, how do you find the fitness value? You use it for classification and see what is the error of classification. Okay, and that will, your fitness function will be 1 minus the error, right? And you could also use it, using the number of features that you have, right? So if you have less number of features, you can get a higher fitness value. Okay, so you can use these two things in your fitness computation, right? Similarly, you can use GA for prototype selection. And so what happens here is that each of the element is one of the patterns in the training example, and you have zeros and ones, right? So a 0 will mean that the pattern is chosen as a prototype, and 1 means it is not chosen, right? And you can also have a GA based backpropagation network, okay, where what you're doing basically is that the weights of your decision tree is being found using a GA. Okay, so you're not going to do backpropagation and update the weights. Instead, you're using a GA to find the correct weights. And the weights which give you the best classification, that is the one which is going to be chosen. Okay, right? So this is a GA based backpropagation network. Okay, not going into details, right? So here this is one work which we did in our lab. So when you are finding distance between time series, you can use different types of distance metrics, right? So here we used 8 different metrics. And what you find is in some data sets, some of them work well and another works well. So what we did is we found a new distance metric where we took a weighted combination of all these eight. And these weights, we actually used genetic algorithm, simulated annealing, etc., to find these weights in this. Okay. So next is the particle swarm optimization. So I won't go into details of how it works because I'm sure that's part of your. Um, so you have patterns in space, and you are moving these patterns to a more optimal position at each time step till you find the finally the best position, right? So that's the idea of PSO, or the particle swarm optimization, and it can be used again for prototype selection, just like we did in the case of the genetic algorithm. Here we are doing clustering and feature selection simultaneously, right? So which means if you have D features, the your string consists of all those D features plus the N elements, right? So these D features will be 0 or 1, whether you're choosing the feature or not. And these N elements will have the cluster number at random at the starting, right? So you're seeing, you're doing both of them together and seeing which one gives you the best value, right? So you find basically that there are a number of applications of soft computing. Basically, I don't want to go into this, and I think I have actually exceeded my time here. So I'd like to say that there are a number of machine learning applications where soft computing techniques have been basically used. And we are also in our lab working on using soft computing techniques for machine learning applications. And in summary, we can say that when conventional tools don't work, then using soft computing tools helps. For example, if you have some optimization problem with a lot of objectives, or you have a lot of variable conditions, etc., then the classical when the classical optimization doesn't work, then you can use this type of soft computing technique. It's good in doing complex optimization problems, etc. Okay, and we have seen a number of applications where machine learning uh, applications where soft computing has been basically used. So I'll stop my talk here.
Thank you, madam. If anyone has any kind of doubts or questions, then they can ask openly. You can unmute your speaker and you can ask questions if you have. No questions?
Uh,
Yes.
Professor Patel,
Yes.
if you can hear me, yes, I want to ask one question.
Yes, you
Yes.
are audible. You can
See,
go
the
ahead.
thing is, you are considering some new distance measures.
Yes.
In general, it is fine because, as an example, I have X, Y, Z. If I want, I can choose X coordinate in centimeter, Y in inches. Or if one is orange and another thing is color, sorry, not color is not a good one. But my problem is that in artificial neural networks,
Yeah.
if you are going to redefine completely to a new kind of access, whether your original weighted data distances, whether it is going to be really good or not. Of course, I am not in the field. Maybe I
So,
have.
what you are basically saying is that if you have features which are not numerical, right?
It does
Uh,
not have to be numerical.
yeah.
Basically, the question is, as an example in mathematics, you
Yeah.
can call a vector based on its certain transformation properties. As long as you maintain it, your this scaling etc. is fine.
Right, right.
If you cannot, that is what probably you are doing it right. I am only as an outsider asking it.
Yeah,
So
yeah.
when you are redefining your distance measures
Right.
with weight,
So that is only in the case of time series applications, and it doesn't have anything to do with neural networks, basically.
okay, fine, all right, okay,
What
okay,
we are doing is that you're trying to find distance between two time series. So
okay,
it's like finding distance between two shapes. Okay, everything is numerical in both, right? It's just that you have more than one point, right? You have a series of points in sequence. So in that case, how do you find the distance between the two
okay,
times?
okay, fine, okay, that's
Yeah.
fine, all right.
Any other questions, if anyone has?
Yeah, so basically, it's a very vast topic, and it can't do much justice in half an hour. So
Yeah.
I just sort of gave an overview of some of the
Yes.
techniques.
Yes, madam. But for like new researcher, it's really useful for them. You have covered that different aspects of the soft computing, and you have differentiated the hard computing and soft computing. That is really interesting thing, and really informative things for the new researchers also. And you have covered the different algorithms that falls under the different aspects of the soft computing, and you also cover the different hybrid approach and of a soft computing. I just would like to just as a for a new researcher, if they want to start working in a soft computing, then what are the main challenges or constraint in that?
Yeah, so I think that all problems cannot be solved by using soft computing. So, for example, if a problem already has a direct approach or a direct solution, you wouldn't go in for soft computing. So, soft computing basically works for only some type of applications. So you need to see whether it is suitable for the application you have in mind, basically. That's
That
the idea there. And also, you need to adapt the problem to the soft computing technique. For example, if you're going to use a genetic algorithm, you have to see how would you represent it, and if you are going to represent it in a particular way, how will you carry out selection, crossover, and all those type of things. So the challenges are to adapt the problem to the soft computing technique, basically. Um, and obviously, you need to see that some convergence is there. You know, those type of things are very important. The convergence is happening, and how many iterations you need to go through, etc. So those things are some things which you need to take into account here. So those are the basic challenges here.
Thank you very much, madam, for sparing your valuable time for the icSoftComp 2021. We are really very grateful to you that you come here and as a virtually and you spare your
Excuse me,
valuable time. Thank you very
sir,
much.
I want to ask one question.
Yes.
That's
Yeah.
for Shali. Ma'am, can we use the soft computing for text summarization, abstractive text summarization? Because in abstractive summarization, when we go through the hybrid approaches,
Right.
so how and in the language model development.
Mm. So basically, in summarization, actually nobody has used, these tools for summarization as of now. But the idea could be to see how you can give weightage to different words, right? Or
Yeah.
different sentences, and choose sentences which have got higher weightage. So
Uh,
can use these techniques to find that weightage for the sentences.
Yeah. But ma'am, what thing happen in summarization? There are two different concepts. In extraction, we can use this model, but
Yes.
can in abstraction we use, because what happen?
Abstraction, you cannot use the weightage thing like I told you.
Yes, yes.
It's a sort of a research field where everything is open, right? You can try to find some technique if possible, right? I don't think anyone has used for abstractive summarization. I don't think they have used these techniques as such till now.
Okay, ma'am.
You could think about it, right? It's a
Okay,
research field. Maybe you can come up with something, right?
okay, ma'am. Okay, okay. Thank you, ma'am.
Yeah.
Thank you very much, madam.
Thank you.
I think Dr. Ghosh is there. Dr. Ghosh, are you there? Yes.
Yes, I am very much there.
Just give me 1 minute. I will make you
Yeah,
presenter.
and I need this sharing
Yes.
access.
Yes. I'm going to make you the presenter. Yes, sir. You can share your content or screen.
Is it visible?
No.
No.
Yes, sir.
It is visible now, right?
Yes.
Okay, good.
Okay. Okay, so next invited talks is by Dr. Ashish Ghosh. He is working with ISI Kolkata. He is associated with Machine Intelligence Unit of ISI Kolkata, Indian Statistical Institute of Kolkata unit. His research interests are mainly in this data science, big data analysis, then deep learning and neural networks, machine learning and pattern recognition. I will not take too much time because we may have a less time to listen him. But if you want to get more details, then you can refer his web page on ISI Kolkata website. I welcome you, Dr. Ghosh, again formally to this icSoftCom, and I am really thankful that you spare your valuable time for this our conference. Now I hand over to you, sir. You can start
Thank
your.
you. Thank you, Dr. Patel, for your invitation for this talk, as well as a very deep introduction. So given this half an hour or so, I will be trying to introduce what is called multi-level classification. This is one of the very challenging topics and emerging topics, I will say. So I will try to give you a rough idea about what is multi-level classification. Why do we need multi-level classification? How multi-level classification can be done? And some matrices or some databases which are usually available to evaluate the quality of multi-level classification. Now, all of us know what is classification. So in classification, what we do is we predict the class level of unknown data samples. We have usually two phases. One is the training phase, one is the testing phase. So for the training phase, I have a set of data whose labels are known to me. And these labels are usually single level, class level. So for example, I say, okay, there is an image and the image is of a dog. There is an image and the image is of a cat. So the label is a single level. The image is that of a dog only, nothing else is there. If there is anything else, that's a kind of background. So that's what is the problem we usually do, say, filtering your emails, spams and non-spam. Identifying handwritten characters. You can recognize 10 handwritten digits, say 0 to 9. So 10 classes. But each pattern or each object will belong to only one class. It comes from only one class, not more than one. That's what is the traditional classification. That's what we are habituated to do. Most of the cases, whatever we mean by classification or whatever we do in classification is nothing but classifying this sort of patterns or objects or images or whatever you call to one of the categories, one of the say n categories or c categories, which we know that there could be so many classes. So that is what we are habituated in handling. Say for example, this is a set of image. The leftmost image is of that of a sand, then it is the image of a sky, and that of the sea. So each of these images can be labeled just with only one class. There is no confusion in this. But if I have an image like this, say the first image, it could be the image of a sky, it could be the image of a sea. You can see that one part is sky, one part is sea. Sky and sand. One part is sand, one part is sky. And there is a mixture of sand, seas, then sky, and so many things. So what is the label I am going to put to this image? Is it a sky? Is it sand? Or is it both? So this is a more complex problem than standard traditional classification. And this is what we are going to handle. This is what is the new thing that has come up recently. That this is a new problem, and with the advent of data, with the advent of this sort of images, we need to classify them. Say if we look at the blogs, if we look at the tweets or texts or news, so there is a news of Navjot Singh Sidhu. So it could be a news related to cricket game, it could be a news related to politics. So multiple labels. Nowadays we have plenty of data where we have so many labels. So many labels, maybe one label or two labels or three labels or whatever it is. This is applicable to almost all kinds of new data that is coming up. So how do you handle this problem? How do you classify each image? Okay, so the data can belong to more than one class at the same time. Mind this, the data can belong to more than one class at the same time. And it is not the fuzzy membership, it is not the degree of belonging. It's not that it belongs to the water class to this extent or sea class to this extent and it belongs to the sand class to this extent. No, it belongs completely. We can put that, okay, this is an image of a sand as well as a land. It's the image of a sand and image of a land, or image of a what is it called, sea and image of sand. So both 1 1. It's not 0.5 point, but it's not 0.7 0.3. So it's not fuzzy membership. So forcefully I cannot assign this image to one of the classes. It has to belong to multiple classes. That's the nature. The nature of the image is something like this. The nature of the tweet is something like that. So we cannot bypass that. So how do we handle this? So basically, multi-level classification is nothing but an extension of single-level classification, or what popularly we call classification. Here also, what we have is the data, standard data, these d-dimensional data, features, but the number of classes it belongs to is, instead of only one, there are n number of classes. So like for normal pattern classification, I say whether it's a spam or non-spam, but there could be an image, there could be a mail which will belong to two, which will belong to both. There are plenty of application domains. Let's say I take the picture of a satellite picture from a long distance. Now one pixel will cover one part of a pond and one part of the land outside that pond. So these two labels I need to put over there. So The label is also a vector. The input is a vector, corresponding label is also a vector. So it's basically vector to vector. Now, this could be handled in many different ways. This kind of data exists, but it was not handled previously, mainly because the multi-level data was not abundantly available, and it's very difficult. With the advent of technology, we are getting more and more data, social media, mobile data, mobile phone, sensor data, and so many things. Plenty of data is coming up. Storage capacity requirement is very high, and the computing power is also needed to be very high. So since nowadays we are having these GPU machines, we are having other devices where we have more storage area, so we can use this. We can now handle this. Look at the application area. I can do a kind of human activity recognition. Given an image, I just cannot say that the man is doing only one job. Let's say one person was eating and cooking. So he or she is doing two jobs. Then maybe one person was jogging and at the same time he was drinking. So doing two jobs. On playing and practicing or jogging, two jobs. So maybe human activity recognition is one field. Remote sensing data. You look at the satellite pictures. One pixel or one image can have water body, can have trees, can have bare soil, can have buildings, pavements, can have airplane, then runway, maybe the airport. So it's not a picture of only one airplane. It could be airport. It could be the runway. It could be the land. Movie recommendation system. A movie can be categorized to comedy movie. It could be drama movie. It could be a family movie. A comedy movie can have two levels. It could be something like a comedy as well as a family. So this way, if I look at, I will see that there are plenty of types where these sort of applications are needed. Okay. Now the complexity comes from here. The multi-level data will have very complex decision boundaries. That is the problem. Like if I consider the sand class, then something on the top of this kind of yellow line is sand. Something on the bottom of this green line is sea. So the boundary is not very clear to me. Or same boundary may not work for classifying two classes but two levels. Another boundary may be needed. So for classifying sand and non-sand, maybe this line could be useful, but this C classifier is also needed because others may not be useful. If using any in this sand level, I can say all the three images have sand category. All the three images on the top of this yellow line has sand, nothing below this. So this line could be distinguishing the sand class, sand and non-sand. But it cannot tell anything about the sea. It cannot tell me anything about the sky. So one and all, one versus all. So there could be many different ways to handle this. Two most important ways of handling this is either we transform that data, so multi-level data is transformed to a single level data, or we adapt the problem, adapt the techniques to fit or handle multi-level data. So two more important issues on which you can work is either you transform the data from a multi-level to single level, or you transform your algorithm or design a new algorithm to handle multi-level data. So data transformation technique is usually very simple and started early. Here how it happens and how it works is each data, say I have a data where I have a sand class as well as water class. So that data basically I consider to have two instances. So I would say, okay, First data instance belongs to the sun class, second data instance belongs to the sky class, or the water class. So basically what is happening? The same data I am using as a training sample for the sand class as well as a water class. So when I will be training the sand class, I will train with one data. When I will be training for the water class, I will do the same job using another sample. So basically, if I have 10 samples, maybe I will have more than 10 samples, maybe 15 or 20 samples, depending upon the number of levels. So this way we can handle the problem, and this is usually referred to as level power set. This is a power set. And using a technique called binary elements, where learn a different classifier for each class. Say for a land class, I train one classifier. For sand class, I train another classifier. For water class, I train another class. So one versus all. So one classifier is trained using the whole data set by considering examples of a class I as positive and all other as negative. So whenever I am training a sand class, I am not bothered about the sand class. I'll say it's non-sign. If I am training for water class, I will say this is the positive example. Rest are all negative examples. So that could be an example of a sky. That could be an example of something else. So this way, this technique is usually called the binary relevance technique. So naturally what will happen, you will have more images or more inputs, although initially you did not have so many, you will have. So large input output dimension. And if there is complex decision space, life becomes very difficult. Also, this has a drawback that it becomes very difficult to handle two classes which are correlated if two classes are very much correlated. Say for example, if you take the picture of a sunset, you are always going to get water and sand. Or maybe if you are in the top of the hill, you are going to get the sun and the hill, or sky and the hill. So they are always correlated. So it is very difficult to distinguish them. Also, we can have a problem like imbalanced data. Some class may have small amount of data, some class have a large amount of data. So depending on the type of the data, depending on the input, different types of techniques are suggested. It could be a binary relevance method, it could be a power set method, it could be other methods also. I'm not going to give you an exhaustive list of all these methods. What I'm going to tell you is the basic idea about what is multi-level learning and how can you handle it. So one is data adaptation, change the data such that it fits to a single level classification. The second one is problem adaptation, or designing a classifier which actually can handle this. So instead of handling this, I will design a multi-level classifier which will classify more. So how is it going to design? Now say for example, tree will be one class, tree and sand may be one class, sea will be one class, sea and sunset may be another class, sea, sunset, mountain could be another class. So all these three together will constitute my one class. So for one image, one instance, I will say this is an example of a sea. So this is one level. So sea is one class. Sea and sunset, this combination is another class. Sea, sunset, mountain is another combination. So what is happening? Although initially we had say three classes, sea, sunset, and mountain. Now we will have 2 to the power n such classes. I will have a class called sea. I will have a class called sunset. I will have a class called mountain. I will have a class called sun and sunset, sea and sunset. I will have a class sunset and mountain. I will have another class sea, sunset, and mountain. So this way, different possible combination of the classes. For whatever combination I have the input, I will say that is a new class. So what is happening? I will have more number of classes. So then what I will do is I will train my classifier assuming these to be different classes. Now, designing such a classifier is usually very difficult. It's not so simple. And until nowadays, different varieties or different proposals have come up. They are tree based, they are neural network based, they are support vector machine based, instance based. So something new is coming in gradually and gradually. This is a very new topic, very new subject. So maybe plenty of scope is there for doing research. Not much research has been done. So what people are trying to do, people are trying to extend and expand the already existing single class classifiers. Using these different sets of data, assuming that either I will modify the data type in the sense that, okay, data I can put into different classes, or segregating the data, or assuming that our data will belong to multiple classes. So the standard decision tree C4.4 is enhanced, is modified to handle multiple classes. And it is giving good results. The same entropy, same gain index, same thing, same criteria used. Only thing is that when I was having only one class, I was using the entropy of that class. Now here I have multiple classes, more than one. So what I will be doing is I will be using this double entropy, or class and not being a class. Being a class and not being a class. But if for a single level classification, I don't need that, I don't do that. So this way I can design a decision tree. Even the multi-layer k nearest neighbor, single layer k nearest neighbor classification model is modified. How? Now you are checking independently that, okay, which class it is predicting. It can, the same data, it can predict to C class, it can predict to water class, it can predict to sand class. Independently, you are taking care of it. Right? The same KNN you are running, one for the C class, one for the C and water combination, one for the C water and maybe sun combination. So then, depending upon that same image, if it says, okay, if it tells you that it belongs to sand, it belongs to sand and water, it belongs to sand, water, and sunset. Possibly, you will assume this that, okay, this has maximum 3 levels. So this maximum 3 level case is more useful because it can belong to all these 3 classes. So this way, things are getting modified. We will compute that, okay, which of these or how many of these classifiers is telling it belongs to more than one class. So what criteria you are going to use is up to your choice. There's no hard and fast rule. These are very new things. Things are coming up, suggestions are coming up on this. And in the testing phase also, you will do that. Neural network, they are usually habituated to handle single levels. So here also, for the same input, I can assign to multiple classes and compute the error from multiple classes. So multi-layer perceptrons are modified to handle multi-level classification. The same backpropagation learning is used. Same thing is done. But only extension is, instead of training it for only one class, you will train it for multiple classes. Now we can even use the ensemble. So I'm not saying that whatever is coming up is very great and very new. What I'm trying to tell you is this is a new problem. This problem needs big attention, and people have already started doing research on this topic, which are nothing but extensions of most of the existing things. So some people have done some modification in one way. You can do modification in some other way. So chain of classifiers are used. Okay, one classifier will do this sand classification, one classifier will do the water classification, another one will do that sunset classification. Right? So some places you can preserve the dependency, some places you may not preserve the dependency. For example, this sunset, water, or sea and sand, they come together. So this I can preserve and say, okay, oh, usually these 3 occurs together. This co-occurrence I take into consideration. And if there is an image having multiple level, I will say, okay, this is the picture of a sunset, because sunset involves all these 3. Rather than saying it is a picture of a sea or sand, I will say it's a picture of a sunset, because that's what we do. We try to take the picture of the sunset only. We don't take a picture of sea and sun, sea and sand. We take the picture of the sunset. So these three come together. So this association, this correlation, we try to preserve. So this way we train a set of classifiers, and preserving this, we can say that okay, this works fine for us. So there will be mathematical modeling for this, how to handle all these sort of things. Okay, we can use ensemble, you can use chain of classifier, we can use random k level. This is becoming very powerful, very successful. Instead of taking all levels, they are taking only random samples, random k level samples. And like random forest, you take a set of features and you take a set of samples. Here also, you take a set of features and take a set of classes. So random k level set is becoming very popular. It is giving, in less time, it is giving good result. So that is becoming more and more popular. Now, so many techniques are coming up. So naturally, there has to be some measures for this. That okay, what are the measures that will tell me that present classification is better than the previous classification? Hamming loss. Hamming loss is that bitwise distance measured, how far it is away from the actual class, how many bits it is differing. Hamming loss is one measure. Classification accuracy is always there, everywhere it will be there. Okay. Then exact match or subset accuracy, that is also there. Most strict evaluation is that exactly matching or not, exactly matching with the level sets or not. Count the number of instances with completely correct prediction. So it depends on you how you want to look at. So obviously, if you want to be very strict, exact match is important. If you want to give a little bit of flexibility, yes, some partial match or subset accuracy is also useful. Or you can rank them. Instead of assigning the crisp level set, a rank of all classes are generated in using the classification scores. Okay, this has this much accuracy, this has much. So it belongs to this class with this much probability, this class with this much probability, this class in probability, and so on and so forth. So this way you can do many things, many levels. These are some of the new things that has come up, but plenty of things need to be discovered. I'm not claiming that everything is discovered. It is no, it's not yet discovered. Plenty of scope is there. And some of the databases that is available is just a kind of a brief thing that, okay, Java library for multi-level learning, the source is this. Then some multiple data websites like Finzi, then variations are also available. Sometimes this multi-level data, rather than giving the full level, sometimes it is given in the form of hierarchy also. First you put one level, say for example I say sunset, then under sunset I set two levels. So it is sand class, it is water class or sea class. So this sort of hierarchical leveling also is coming up. So whether you want to give a hierarchical leveling or you want to give a perfect leveling to that is up to your choice. Or you can use extreme classification. So they are exactly matching or not. Okay. So these are some of the new things that have come up. I tried to give you a glimpse of that. That the multi-level idea that okay, this is multi-level problem, which is a more difficult problem than a single level classification. And to put you or give you a little more information, I can more or less inform you that although multi-level classification is available, multi-level clustering is not that much available. So this is one of the very green fields available if you would be willing to adventure into this, because it's very difficult. You do not know how many levels you want to put it to. So multi-level clustering could be one of the very interesting topics where you can venture. So maybe with this brief introduction, I will stop my presentation here. If there is any question, I'll try to answer. Else, thank you. Thank you so much for listening to me to this new ideas or new research topic that is coming. Thank you so much.
Any questions from audience?
Sir, if I could ask you a naive question.
Please.
See, the thing is, suppose as an example, you have a set of humans. You put their weight, height, and let us say skin color. If they are independent, the way you define the entropy, etc., I have no problem. But possibly, as an example, an Indian may be systematically underweight compared to those from Netherlands or so, but you may not know this relation beforehand. So I was pondering whether your multi-level entropy, whether it is a good measure. See, I am not from computer.
I understand. Thank you. Thank you. That's a very nice question. uh, for this sort of cases, what happens is there is something what is called contextual classification. Uh, that is very common in this sort of machine learning things. Some places, some features are useful. Some places, some features are not useful. For example, if I want to distinguish, say, Bengali people from Odia people, complexion cannot be a good feature.
Right.
On the contrary, if I want to distinguish Indians from, say, Europeans, complexion could be a good feature. So there is some topic called feature selection. So depending upon the context, some features may be useful. So before you are coming to this classification stage, there is something called pre-processing. There you will have to think of that, okay, this is my purpose, whether this feature is useful or not, and design the feature or extract the feature accordingly. So that could be one of the pre-processing you need to do.
Okay.
And also, as I pointed out, this entropy is defined does not necessarily mean that is the best measure. We can come up with something better than that also. Because this is a very new field, innovative field, it's just coming up. Things are being tried. It's not completely exhausted, nor is a mature field. So plenty of scope is there to try out.
Okay, thank you, Ghosh.
Anybody else? If you have any questions. No questions? Sir, I would like to know where exactly we cannot use this multi-level classification, like for which kind of applications or for which kind of data set where we cannot use this multi-level classification. Is there
Oh,
a
yes, yes, there are plenty. There are plenty. The most of the classification problem that we handle nowadays is single level.
yeah.
Almost 90% or maybe 95%. And the data set has only one level. It does not demand any multi-level. Say spam filtering. It is either spam or not spam.
Yeah.
It cannot have a combination. So we do not need multi-level. Say human being and non-human being. By its very nature, it is single level. We cannot put multi-level. Only there are few places. Say I have taken the picture of a forest. Nothing else is there. So I cannot put more than one level. There is no sky. So only if multiple types of classes are there, only in those situations multi-level classification could be useful. That also may not always be useful because usually what we do is we try to take some subject with some background. And we usually bother about the class of the subject, not bother about the background. So in this situation also, we may not be interested in using multi-level learning. So it's not that multi-level learning is mandatory. What I'm trying to point out is there are places where multi-level classification could be used. Not all places.
Any questions from our audience? Okay, sir. I think there is no questions from the audience now. Okay. So actually we are behind the schedule and we need to skip our break
Yeah.
also, right? And the other invited speaker is also ready. So, Dr. Bose, thank you very much for sparing
Thank
your
you.
valuable time for us. And you have discussed on a topic that is really interesting and very new topic that researchers can carry out in this kind of new topic, that is multi-level classifications. And you have covered the different approaches that we can use for the multi-level classification, and you also cover the scope of this research, then challenges that we can face in this kind of research, we can have in this kind of research, and you have cover also the different evaluation techniques for this multi-level classification, and you also cover about the data sets that we can use for the multi-level classification. Thank you very much, sir. Thank you very much
Thank
again.
you. Thank you, Sanjeev. Let us keep in touch. Okay. Thank you.
Yes. Dr. Singh, are you there? Dr. Singh, Pritpal Singh, I made you the presenter. You can share your screen. Yes, sir. Your screen is visible. Okay, sir. So, formally, we are welcome you, Dr. Singh, to this icSoftComp. Dr. Pritpal Singh is working as an adjunct professor at Institute of Theoretical Physics in uh, University of the one of the University of Poland, very well-known University of Poland, BC. And his main research interests are ambiguous set theory, then quantum optimization, image processing, and machine learning. The title of his talk in this is ambiguous set theory and overview. Dr. C, you can start your presentation. Please unmute your microphone. Your microphone is
Okay.
mute. Okay.
Okay, now it is okay?
Yes, it's okay. We can. You are audible.
Yes. Now, good afternoon, everyone. My today's presentation topic is ambiguous set theory. Currently, I'm working as an adjunct professor in the Agulalian University Institute of Theoretical Physics. Previously, I was also associated with National Taipei University of Technology, Taiwan. Now, come to the main topic, which is ambiguous set theory. Ambiguous set theory, it is a completely new kind of set theory which can be considered as an extension of fuzzy set theory, and intrinsic fuzzy set theory and neutrosophic set theory. So this idea was first published in IEEE International Conference on System Man and Cybernetics in 2019, in which conference was held in Italy. So in this article, you will just find the philosophy of ambiguous set theory, how this idea was evolved in our mind, and some properties, some definition we have proposed in this article. But due to limitation of conference proceeding, we just summarize our work within a first 6 pages. So, but no, we continue. But I continue work on this theory, and it took me around 2 years to publish this work in a reputed journal. I will discuss this in the next PPT. So first, come with the overview of our presentation. First, we introduce the notion of ambiguous set theory. What is ambiguous set theory and how mathematically it can be represented. Second, we present the how to compute the membership. Ambiguous membership functions can be defined. So in ambiguous set theory, we have 4 different membership functions. One is true, second one is false, third one is true ambiguous, and fourth one is false ambiguous membership. So with these 4 membership functions, we can define the membership of any event. Third, to quantify the inherent ambiguities using the ambiguous set theory, how to compute the how to quantify the uncertainties associated with the ambiguous set theory. So we propose the formula of entropy in this research work. Now this fourth we have proposed the ambiguous D means fusion clustering algorithm, and this full-fledged work on the ambiguous set theory with its mathematical definition, notations, and its real-time application, like designing a clustering algorithm using ambiguous set theory. All these are proposed in this knowledge-based system, one of the reputed journal of the computer science domain. And recently this article was published. Fifth one is our contribution is we apply the ambiguous D means fusion clustering algorithm as title suggested in this article. We applied this a clustering algorithm in the CT scan images of COVID-19 patients. The main objective is to cluster the grayscale values of these images in such a way that correlated features of the infected regions can easily identified. That means our objective is very clear, to distinguish the infected regions in the CT scan images of COVID-19 patients. Because you know that the CT scan images which are related to especially COVID-19s are not clear. They have a very they contain lots of noises in these images, and quality of such images are not so good, because these images are captured by most of the time the people these images capture are not so expert, because we have lots of patients of COVID-19 patients. So these images are captured by the novice people or non-expert people, and the room in which these images are captured are not maintain the visual quality. That means there are no proper darkness maintained in these in the room where these images are captured. So we will find the very poor quality of these images. So to extract the features from these images are very difficult. So just we tried to apply our algorithm in these images, and we received and we got the very good results. Later I will show all these results in this presentation. First we start with the philosophy of ambiguous set theory. According to the Oxford Dictionary, the word ambiguous is an adjective that means open to more than one interpretation. That means we can give more than one representation to any event. We don't focus on precise kind of representation of a particular event, as in the case of fuzzy set theory. That means in the fuzzy set theory we have only one representation of an event, that is true true degree of membership. There is no other option in the fuzzy set theory. But in case of ambiguous set theory, we have a scope to represent the interpretation, to represent the event with more than one interpretation. Some information reflect different interpretation, which leads to the ambiguity and incompleteness. So that means events are not clear. So how to define their ambiguities? It is very challenging task. So as a result of this problem, decision makings become very difficult in most of the cases. So for example, consider this proposition: Mr. X is lying. This is the famous proposition in the philosophy, that Mr. X is lying. Now how to characterize this event? This statement is, as a human being, we can consider this statement as either true or false. We have no other option, that Mr. X is lying. You consider this as a true, otherwise you consider this statement as a false. So in view of the proposition, the human cognitive process can have the following perception. For example, perception 1, that we consider that Mr. X is lying. Then another perception which evolve in human mind, that Mr. X is not lying. Now, perception 1 and perception 2 can have definite true and false value. For example, consider perception 1 as a true and consider perception 2 as a false. So however, there is often uncertainty and incompleteness between truth and falsity. That means we have a scope that we can define some ambiguity, some incompleteness between this true statement and false statement. So according to this, so we more discretize this perception 1 and perception 2 in the form of perception 3 and perception 4. According to perception 3, we assume that Mr. X is a little lying, and another perception 4, that it is a little false, that Mr. X is lying. So we generated another two perception from perception 1 and perception 2, that is perception 3 and perception 4. Now, perception 3 and 4 cannot have the distinct true and false value. It is clear that Mr. X is a little lying, so we cannot consider as a completely true. Similarly, perception 4 cannot be considered as a completely false, because it is mentioned that it is a little false. So perception 3 is very close, but it is clear that perception 3 is very close to the perception 1, and it inherits the ambiguity from perception 1. So it can be categorized as a true ambiguous. So it can be considered as a true ambiguous. That means perception 1 is clear, completely true, but another perception, that is perception 3, which is evolved from the perception 1, can be considered as a true ambiguous. Now come to the perception 4. Perception 4 is very close to the perception 2, but it develops ambiguity from the perception 2. That means perception 4 is directly evolved from the perception 2, so it can be represented as a false ambiguous, because perception 2 is considered as a false. So a perception which is evolved from the false statement or false representation of uncertainty can be represented as a false ambiguous. So it indicates that any event E can be viewed in terms of following four different perceptions. That is P1 and P4. For P1, here P1, in the P1 event E is completely true. That means we consider E as a completely true. P2 perception E is completely false. That is false E. P3 is a little true, so it is considered as a true ambiguous, and P4 is a little false. So the P4, that means in case of P4, event E is a little false, so it can be considered as a false ambiguous. Now, by integrating now how to integrate these four perception into a one set, or it is another problem, because now we have a 4 dimension of a single event. That means for one point or one event, we have a 4 different kind of visualization, we have a 4 different type of perception, we have a 4 different types of cognitive effect in our mind. So how to integrate these 4 perceptions together? So this integration is nothing but a new kind of theory or new kind of definition I have proposed, that is called ambiguous set theory. This is completely new. So yeah, there are lots of scope in this theory. We have communicated 3 or 4 articles in the reputed journal which are under review. Main problem is, as this theory is new, so it is very difficult that journals are accepting this article as for reviewing purpose, but luckily the articles are under review. Hope so it will be accepted, and then you can get the benefit from this new kind of theory. So according to this theory, the initial perception of the event are characterized as a true and false. The ambiguities in true and false are characterized by the perception true ambiguous and false ambiguous. The ambiguities in true, false, true ambiguous and false ambiguous are defined with respect to 4 degree of membership functions, which are true, false, true ambiguous and false ambiguous. So based on these 4 representation of event, we have proposed the 4 membership functions. Using these 4 membership function, we can define the degree of memberships of any event. So now come to the technical definition of the ambiguous set theory. Ambiguous set theory is nothing but I suggested that it is the combination of true, false, true ambiguous and false ambiguous membership function. So for any event X in the universe of discourse S, that means we have an event which belongs to the certain boundary or certain universe which is S. So now characterize this X using the true, false, true ambiguous and false ambiguous. So ambiguous set A on the universe of discourse S can be defined based on the 4 membership, where each and every membership function's value should lies between 0 and 1. And remember that membership function value never be less than 0, that never be negative, and it never be crossed to the value of 1. So this limitation indicates that all these membership value should be lies between 0 and 1, and this membership function must satisfy the condition that sum of true, false, true ambiguous and false ambiguous, if you take the summation of all these membership functions, it should not cross to the +2. That means this is the restriction of this theory. So if there is something wrong in the definition, in the computation of true, false, true ambiguous, false ambiguous, and if you take the summation of all these membership function and their value cross to the +2, then you just come to know that there is something wrong in the representation. So that's why with we put this restriction here. Now, how to define these membership functions? We proposed one formula in this article which is published in the knowledge based system. So we have proposed many formulas which are under review to how to define the membership functions. So consider X is an event, and its true degree of membership can be computed with the help of this formula. X, take the value of X here, numerical value, minus mean, to compute the mean from the whole universe divided by max of whole universe minus mean of whole universe. You will return a single value of a particular event X, and this value must be lies between 0 to 1. So definitely you will get the value between 0 to 1 using for the true degree of membership. Now come to the false. So if something is false, that if how to define the false? False is obviously it is totally opposite to the true degree of membership. That means it is completely contradict to the true degree of an particular event. So false is defined as 1 minus true degree of membership. That means we just subtract the true degree of membership value here. We will get a one single value, which is again its value lies between 0 to 1, because we are subtracting from the 1. So now come to the true ambiguous. True ambiguous, I already mentioned that if this true ambiguous is evolved from the true degree of membership, so it should be defined based on the true degree of membership. So true ambiguous equal to whatever we get for the true degree of membership, we put here divided by true degree of membership plus a f of x. This is another pair function which is defined in the below. So we come to the how to define the false ambiguous. False ambiguous of a particular event x is defined based on the true false degree of membership, because false ambiguous is evolved from the false degree of membership. So false ambiguous equal to false degree of membership divided by false degree of membership plus a of x. So how to define the af of x, which is used in the third equation and the fourth equation? So af is termed here as the ambiguous distance function. This is ambiguous distance function and can be formulated as true degree of membership is square plus false degree of membership. That means take the input from the equation 1 and from equation 2 and do the square root of both the values and compute the square root. You will get one single value, and you put this value in equation number 2, equation number 3 and equation number 4. So in this way we can define the for the numerical value of a particular event, and all this numerical value is considered as the true ambiguous set. That means these four values can be considered as a member of ambiguous set. So this is the basic idea behind the ambiguous set theory. There are lots of scope to define the ambiguous membership functions, because this is the basic idea. But I am not saying that this formula is very good, because we have proposed more advanced formula for the true degree, true, false, true ambiguous, and false ambiguous. Now, to take the one numerical example, first ambiguous representation, how to represent provide the ambiguities for a particular event. Let us consider two different ambiguous sets, A1 and A2. For the grayscale, consider any grayscale value where vi, that means any pixel belongs to the image x image, and ki is a pixel which belongs to the y image. That means we have two different image, one is x image and another one is y image. Vi is a particular pixel which belongs to the x image, and ki is a particular pixel value which belongs to the y image. And we have ambiguous set A1 and A2. A1 ambiguous set A1 is used to define the ambiguities which belong to the xi image, and A2 set is used to define the ambiguities which belong to the yi image. Defined now, we should define the universe of the image. So you know that in a grayscale image, the minimum value is 0 and maximum value is 255. So we have our universe is defined between 0 and 255. We use this G upper. That means we make it as a generalized. So for example, this image may be not a grayscale image, it can be a color image. So your universe should be defined based on the RGB scale, red, green and blue. So I make this generalized, which is G upper. So U equal to, but at this moment consider as a grayscale image, because CT scan image all are in a grayscale image, because in later section I'm going to show the real-time example of clustering on the CT scan images. So consider this as a grayscale image at this moment. So U equal to 0 and 255. The ambiguity type representation of A1 and A2 as A1 equal to true degree of membership of a V1, that means any grayscale value which is associated in image xi, then compute its false degree of membership, then compute its true ambiguous, then compute it false ambiguous. Now this plus is not a plus, the general mathematical plus operation. This is the union operation. So now we come to the next grayscale value, which is V2 in a same image, xi image. So now compute its true degree of membership, false degree, and true ambiguous degree. Because now in this way we have n number of pixels in a particular image, so we can compute their true degree, false degree, true ambiguous, and false ambiguous. Now come to the image y image. Its grayscale value is gray pixel is represented by ki, and this pixel have a grayscale value for example k1 k1 grayscale can be characterized with the true degree of membership, which is FA to K1, TA to K1, and FA to K1. So in this way, for the second image, we can define the ambiguous degree of membership. So whole matrix, the whole matrix of the y xi image one, yi image can be transformed into the ambiguous set. And now consider, sorry, here I put the neutrophobic type. It should be ambiguous type. So ambiguous type representation of A1. So we have a 4 degree of membership. Remember, 0.20 it is true, 0.97 it is false, 0.97 it is true ambiguous, and 0.3145 it is false ambiguous of a grayscale value V1. Similarly, for V2, we have a 4 degree of membership, and similarly for A2, if ambiguous set, it has a grayscale value K1, so it has another 4 degree of membership, and K2 image have another 4 degree, K2 grayscale value have another 4 degree of membership. Now we can compute the distances between A1 and A2 using the Euclidean distance. I saw this Euclidean distance computation here because in the clustering process, basically we use the distance measurement between the two different points. So it would be helpful to understand this. So how to compute the Euclidean distance? Take the point from the A1 and A2. First value is 0.20. That means 2 degree of membership of A1 minus 2 degree of membership from A2. Similarly, take the false degree of membership from A1 image, A1, and similarly take the false degree of membership from A2. Similarly, take the true ambiguous from the A1, which and so to subtract the true ambiguous value from the A2. Similarly, take the false degree of membership from A1 minus the false degree of membership from A2, and take the square, and lastly compute the square root. You will get a single value which is 0.5528. So the distance between the ambiguous set A1 and A2 will be 0.5528. So in this way we can compute the Euclidean distance between the ambiguous set theory. Now come to the real time example,
Sir,
which
sorry
is
for interrupting you.
yes.
You have 2 minutes more. Please, could you complete it in the 2 minutes?
Oh, I have 2 minutes. I passed the 25 minutes. Okay.
Yes.
Okay. Now
Actually,
just
our
okay.
next session is at 3:15.
Okay, no issue. No, okay. Take the real-time example. Here is the city scan image. Consider a pixel 215, pixel grayscale value 228, and grayscale value 240. We have we have defined the ambiguities between the range 0 to 255. Look at this. Here is the 4 degree of different membership values of 215, 228, and 240. So in this way, we can transform the whole image into the ambiguous set theory. Now, how to quantify? So we already asked that we use the entropy formula. So just use the Senham entropy at this moment. So for the 2 degree of membership, we use that minus t of x into natural log of 2 of x. Similarly, we compute the minus f of x into natural log of f of x. So in this way, we compute the true, false to ambiguous, and false to ambiguous entropy. So as time is very short, so I don't want to discuss this clustering algorithm. You can go through this algorithm from my article. So I want to skip this point, but yeah, I am going to show you the experimental result. uh, look at this, our clustering results of look at this. This is the original image. A is the original image, B is the ground truth image, C is the C is the image which is often yeah,
Pre-processing.
C is the pre-process image. That means we just remove the noise using the Gaussian filter technique, and D is the image which is obtained with the cluster number 3. E is the image which is obtained with the cluster number 4, and F is the image which is obtained with the cluster number 3, cluster number 4. So in this way, we can obtain different number of clusters images. So we can see compare this F image with the C image. We can see the how the image quality is improved, and we can easily get the features from the CT scan images. Now visual analysis. Look at the outcome of each in the each image which is another result of clustering. Here you can also see the features perfectly. So cluster analysis, again here we can in the image H we have compared result of C, D, E, F, and G with the existing algorithm like KMC, K means, fuzzy C means, generalized fuzzy C mean, intrinsic fuzzy C mean, nitrosophic based clustering algorithm where, and H is our proposed method. So we can you can see the quality of the result generated by the our proposed method. Similarly, in the H we will get the quality of our result. Now we have to use the MSE to compute the accuracy of result. MSE value should be very low if your algorithm is perfectly working. So this pink color, you can see that our clustering algorithm mean square value is very low. So we can see that our algorithm is perfectly perform very well. But PSNR value should be very high in case of a proposed algorithm. So here you can see the PSNR value is very high in our image in case of our algorithm. So we can say that it is working perfectly. Now dice the similarity coefficient for the proposed algorithm, dice similarity coefficient value is very high. It indicates that our algorithm is
Sorry, sir.
just
Again intervening.
yes,
Please.
yes, just finish, just. Now, in this study, ambiguous set theory is discussed. Ambiguous set theory can be considered as an extension of fuzzy set, intrinsic fuzzy set, and nitrosophic set. We have applied these images in the COVID-19 CT scan images. In future, we can apply this image in X-ray, MRIs, and remotely sense high satellite images, and we can use apply in other kind of images. Now, my presentation is end. Now you can ask any questions related to this presentation. Any question? Mm,
From audience, if you have
Sir,
any.
I have one question.
yes,
Yes.
yes,
Yes, sir.
yes. You can
Good
ask.
afternoon. Sir,
Yes, good.
I want to ask, in case of languages, because language also creates ambiguities, so how we use this distance function? In same formulas we can use, or how we consider all the things in case of languages,
Language.
language word ambiguities.
The language because you need to define the first define the boundary of the boundary of the language. Language does not have the boundary. So how to define the boundary? For example, he is a very nice person. So how to define the quality nice between certain universes? So for define the ambiguities or define the uncertainties, first you know the boundary of the event. So I think language does not have any boundary. If you can measure the numerical value inside the inside the language. For example, water is very hot, so you can measure the hotness of water. For example, it is between 80 degree to 100 degree. So hot can be defined using the ambiguous set theory between the universe 80 to 100. So it is possible if you have a numerical value, but if you have no boundary, so it is very difficult.
Okay,
I think
so
you
we,
are getting. I think you
yeah,
are
we
getting.
can use this model. Okay.
Yes.
Yes, sir, I want to ask, we can use this in
Hello.
binary conversions. When we go through hybrid approaches, then yeah, certainly we
Yes.
can use,
y-
use this in case of languages also.
Yes, yes, you can use this in any case. In time series forecasting, we are working on time series using ambiguous set. We have working on another clustering algorithm. Anywhere you can apply. Wherever fuzzy set theory is used, you can use the ambiguous set theory as well. So there is no problem. But you need to define the ambiguity using the ambiguous set theory. Yes.
Oh, thank you, sir.
Yes, yes, yes. You can mail me if there is any problem, or anyone, if you want to collaborate for future work regarding the ambiguous set theory, or not only ambiguous, any kind of. I am available for the collaboration. So you can write mail and start work if you interested in the research. Yes.
Yes, sir, I want your help. So will you please share your email ID for us, sir?
Yes, this is the email ID. They just in the first page, Dr. Pulit Palsing 82 at the rate of the gmail.com.
Okay, sir. Thank you, sir.
Yes, yes.
So because of the time constraint, we could not take the next question, sir.
Yes, no issue. Yes, yes, yes.
Okay. So thank you very
Okay.
much, sir, for
Okay.
sharing your like research with us, and very good topic, latest topic, or means new topic that you have covered, that is ambiguous set theory. It's really informative and really useful for the new researcher, those who want to use this kind of theory or technology for their research work. Thank you very much, sir.
Okay. Thank you, sir. Thank you. Thank you. Thank you.
Dr. Krishan Kumar, are you there? Krishan Kumar?
Yes, sir.
Yes, just a minute, sir. I'm making you the presenter.
Hello. Yeah,
Yes,
please.
just a
Please
minute.
proceed.
Yes, sir, you are now presenter. You can switch on your video also, camera also. Turn on your camera if you want. Yes, sir. Yes, Dr. Kumar, shall we start with our next technical session?
Yeah,
As for
please go ahead. Please proceed.
Thank you, Dr. Kumar. Okay, before that, I just would like to tell that Dr. Krishan Kumar is working with NIT Uttarakhand, NIT, and his main research interest is using machine learning and deep learning for these wireless communication and networking. Other research interests are 5G and 6G wireless network, then spectrum sensing and allocations, vehicular network, and he has published a good number of research paper in Web of Science. Scopus and SCI Index Journal. I welcome you, Dr. Kumar, to this icSoftComp, and we are really thankful that you spare your time for this icSoftComp.
Yeah, please. Thank you. And please proceed and start the presentation. It will be very grateful to me.
Right. So, sir, in this technical session, we have three papers. I think you have schedule. Do you have schedule? Okay, sir. So, we have three papers in this technical session. One paper is presenting the one author of one paper is presenting that paper live, while author of other paper is having like a pre-recorded video, and one author has not given any response whether they are presenting their paper live or pre-recorded paper. So first live paper, that is a 170. Is author of this 170 is present over here?
Yes, sir.
What's your ID, team ID? What's your name?
Uh, Rishikesh.
Okay, just a minute. Rishikesh, what is your team ID?
I'm not too sure. My paper ID is 170.
Yes, that's I know, but I couldn't, or just you raise your hand if it is
Oh,
possible.
1 second.
Oh, okay, I find it.
Oh, yeah.
I'm making you a yes. Okay, thank you. Just a minute. Okay, I made you the presenter, so you can
Okay.
share your screen.
Yeah, 1 second, sir.
Rishikesh, you have 12 minutes to present your paper, and after that, 3 minutes is for question answering.
Sure. Is my screen visible, sir?
Yes, it is visible.
Okay. So basically, my last year thesis project was basically a paper based on microstructure image classification of materials using texture features and machine learning. The basic concept behind it was to bring out the relationship between material science and data science. This was done with the study of micrographs, which is basically your microstructural image data. And these micrographs were used to study classification of materials such as stainless steel, mild steel, aluminium, and copper. So to begin with, the objective of the thesis was, like I said, just to classify the metals such as the stainless steel, mild steel, copper, aluminium, using machine learning techniques, image processing, and computer vision. So the samples, everything was prepared from scratch. Everything was done from our side. We used sheets of 13 to 30. We cut it into, they were 1 thickness of each material. It was cut into 10 samples for each material of 2 into 2 centimeter each with 1 thickness, and further fixed into PVC pipes using modeling clay, and further grinded using the polishing paper. And then we had the images taken on under the microscope, and prepared a data sets of approximately 500 images per sample, and further use these for our classification. So in simple terms, just to put out a summary of the model that we have prepared, it was the major focus was on machine learning, and further it started off with image pre-processing, then extracting the features and classifying these features based on the five different classifiers: support vector machines, KNN, decision tree, knife base, and XGB boost. In simple, just a branching. These are the steps for traditional machine learning based methods. You collect the data, you pre-process it in terms of, let's say, equalizing the contrast, histogram equalization, denoising the images, so that our image data set is at a same standard, and it gives more accurate result. For this, there's image segmentation which takes place, and feature extraction, and further there's material identification. So features are basically, in simple terms, they are the parts or patterns of a material which help in characterization of the image. Feature, there's two types basically: feature extraction and feature selection. In feature extraction, we take the existing features and rank them in the order of relevance. In the case of feature selection, we discard the irrelevant features from the model. Over here, we've used feature extraction to prioritize the features which are relevant to us depending on the model. And at last, we identify the material and classify it. So yeah, as I was saying, image pre-processing, the image is inputted into the language, and we further resize it, remove noise, and perform an histogram equalization on it. So this is just a summary of how an image would look. So this is the images. The first image that you see was the microscopic images that we obtained from the microscope that we had, and further the noise was removed, denoised, and there was an histogram equalization performed using a cumulative probability function. And these are the final pre-processed images. So this is for one material that you are seeing. So for one material, there were approximately 500 to 600 images. So there were in total 2,500 images. Feature extraction. So there were eight features that were extracted. Four of them were the first order, four of them were the second order. There's mean, there's standard deviation, there's skewness and kurtosis. I think mean and standard deviation is pretty simple term. Skewness is basically the degree of asymmetry around the mean of the histogram. And kurtosis is the measure of the histogram sharpness. And but the issue with the first order statistics that lie is that first order statistics don't give relevant information about the different positions of the gray levels within the image, which is why we move on to the second order statistics, where we use co-occurrence matrix, which lets us know how frequently two pixels appear in a particular window. Let's say they are placed at a distance of d and placed in a direction of an angle, let's say theta. And from the gray level co-occurrence matrix, we calculate energy, contrast, homogeneity, and correlation. So this is just a sample of how the data was received. Yeah, this is just a sample of how the data was received. So the pre-processed images were inputted into the. Hello.
You may continue.
Okay. Yeah. Sorry. So the pre-processed images are inputted into the programming code, and further a feature vector for the first order and further for the second order is determined, and these are basically used as our data sets and our data for further classifying these images using our classifiers. Lastly, we have the classifiers. So classifiers in simple terms are algorithms which are inputted into the program to help develop machine learning models with the rules for the models to follow. These classifiers, they predict the classes based on the features that we provide to them, and the end result that we obtain is the model that is prepared for the particular problem. So we basically have six different sorry, it's five different classifiers that we use. Support vector machine, which is so support vector machine builds out a hyperplane across an n-dimensional space, where n is the number of features that we used, and data points are built according to the hyperplane, and the plane separate these classes. Further, we have k nearest neighbors. In the case of KNN, it is basically a non-parametric machine learning function which assumes a similarity between new data and the available data, and puts the new data into the class which is the most similar. And k refers to the number of neighbors here, basically. Naive Bayes, in simple terms, is family of algorithms which work on conditional probability, basically the Bayes theorem that we have. and decision tree is the most simplest and straightforward technique that we have, which represents a tree starting from a root node, followed to a stem, to a branch, and further on. Yeah. So in the classification reports, we receive five different results in the report for each material. We have accuracy, which is the fraction of predictions that our model got right. Then we have the precision, which evaluates the accuracy for positive predictor predictions. Then we have the F1 scores, which is weighted harmonic mean of precision lying between range of 0 to 1. You have F1 score, which is basically, sorry, you have support, which is the number of actual occurrences of the class in the specified data set. And lastly, you have the recall, which measures the ability of the classifier to find all positive instances. So we've used two different types of modes for getting a results. Basically, it was a more of a experimental or a trial basis that we had run. So there was there was a normalized mode case and there was a non-normalized mode case. Normalized mode case is basically where the data set, all the whole data set was normalized to ensure that all the images are similar. This is basically contrast changes that we made to just ensure that there's no drastic changes between the data sets of a particular material. And in the case of non-normalized, it was the same as we had received from the optical microscope itself. So in the case of normalized mode, we had changed the pixel intensity values and made it to a constant or close to constant mode. And further, we use two types of evaluation: holdout method and k-fold cross validation. In holdout method, the data set is divided. We divided into two separate sets, which is called the training and testing sets, and the 80-20 method was used. And in k-fold cross validation, the data sets were split into k separate groups. Over here, it's 10 separate groups, and for each group, it was split into training and testing data sets. Yeah, so these are just a summary of the classifiers that we used. This is for normalized mode and a holdout method. So I'll just go through this once. This is for normalized mode, tenfold cross validation. This is just the accuracy F1 score. We've XGB boost gives us the highest accuracy over here. In normalized mode, holdout mode, again XGB boost, and there's random forest as well, which gives out the highest accuracy. And again normalized. Yeah, so just to summarize everything, in the case of machine learning based methods, XGB boost classifier and random forest classifiers are observed to be the top two classifiers. They give out an accuracy of 95 and 93% respectively in the case of holdout method, and 98 and 96% respectively in the case of tenfold cross validation method. Similarly, in the case of non-normalized, XGB boost, decision tree, and random forest show the highest accuracy. So, on a concluding note, as we know, see, the world is moving into a digitalization era. There's everything is becoming automated. Even the smallest things that we can think of is turning into an automation process at this point. So, this is something that we thought would be a great initiative towards the development of automated systems in terms of texture features or machine learning classifiers, or using these in factories just to ease out the work. Yeah, so basically, it presented texture features as effective descriptors to classify microstructure images of mild steel, stainless steel, aluminum, and copper. So further, we found something more interesting was to investigate the use of deep learning models and probably even more transfer learning models for identification and classification of these microstructural images, and to see how they prove their effectiveness towards this. That's it. That's the references. That's it from my side.
Yeah, presenter.
Yes, sir.
Uh, I have some doubt in somewhere your the list of metrics, that is accuracy and F measure is quite similar, but some of the cases like Navy Bezier somewhere it is zero point 0.6 and 0.57. Why this is different? However, the formula you have opted for accuracy and F measure for same.
Okay.
Many
So,
cases out of five classifier, I
okay,
mean, 4 has the same score, accuracy as well as F1 measure.
correct. Okay, so basically, let's say XGB boost decision tree might be on a similar process, but what happens is that how do I put this? The branching towards the end of in the case of the classifier, it differentiates them, and that is what is proving out to be, because the images that we also received, that we took, were also not of the greatest quality, to be very honest. So there was a lot of pre-processing, there was a lot of optimizing of these images that was done. So there is not 100% guarantee that all the images are static across
No,
the data
presenter,
set.
this is, I think you are not following the question. But I said that the accuracy and F measure in
Okay,
many classifier is the same. However, for one or two, it is not same. Either the formula is applied for the same, yes?
correct. Formula is applied for the same. So probably it might be static in the data set, sir. So because in the case of holdout method, we are not splitting the data sets, right? In the case of tenfold cross validation, the data sets are split into 10 different pieces, and further it is put on into 80/20 method.
Okay, thank you. Thanks for the addressing the concern. Thank you.
From audience, if you have any questions.
Sir, I want to ask one thing. What is the role of a random forest in this task?
Sorry, hello. Sorry, I couldn't hear you.
Sir, am I audible? You
Yeah,
are
it
hearing?
my Wi-Fi was just
Sir, I want to ask why you use random forest for this task.
okay. So basically, there was no structured classifier that would guarantee, that we had and guarantee that, this would give out the perfect result. There was not a defined path that we had. As we moved one step ahead, there our issues grew, and moreover, we had to try what do you say trial hit and trial method for each of the classifiers to see how they are responding to these to the models. So what the classifiers that were relevant to the solution is to the problem is what we applied and saw the results that were coming, and put out the results of those.
Okay, okay. Thank you, sir.
Yeah, it is similar to decision tree and XGB boost if you put it, just that as a trial method is what something we put it out as.
Any other questions? Dr. Kumar, shall we move to the next paper?
Yeah, please proceed.
Thank you.
Thank you, sir. Thank you, sir. Thank you for your time. Uh, yeah.
So, is author of paper ID 150 present over here?
I'm sorry, I have organization question. I am author of paper ID 115. I am a little confused about the time zone difference. Did I miss my presentation? I
Okay.
after 115 paper ID.
Do you want to present right now?
Uh, I am ready to presentation now.
Uh, uh, if you want to present, then it is the right time that I can make you the presenter to present your paper.
Uh, yeah, I have pre-recorded video.
Okay, okay. That I
Uh,
know. But
I can start
live
now.
presentation,
I'm sorry.
Do you want to present your paper lively, or I can play the pre-recorded video?
I have pre-recorded video.
Okay, I'm playing that.
Okay, thank you, thank you. Okay.
Okay, so next paper is a 115. That is a modeling of the cost type fractal wire dipole antenna with the random forest algorithm. Just a minute.
Version. I'm from Russia, Kazan Federal University, and I would like to tell about the modeling of the Koch-type fractal wire dipole antenna by machine learning approach based on the random forest. Wire dipole antennas have a wide application from radio communication systems to GPS antennas in your cars. However, the problem of designing a small-sized antenna with required electrodynamic features exists. One way to solve the problem is fractalization of geometry. Therefore, in this study, we considered Koch-type wire dipole, which has an arms geometry similar to the first-order Koch-type refractal. Arms geometry differs from the classical Koch fractal only by the position of the central vertex. In the slide you can see three first iterations of Koch-type fractal. The first iteration is the black curve, the second is the green curve, and the third iteration is the red curve. The rule for generation of similar curves we defined using the iterative scheme based on affine transformations of the plane. It's useful to note this approach allows parameterization of the geometry, such as the use of the number of iteration and central vertex coordinates for unambiguous definition curves in our dataset. It's the opportunity to reduce the number of features in future machine learning algorithms. Let's consider two types of modeling problems, direct and inverse problems. The direct problem is prediction of electrodynamic characteristics from features of antenna radiator geometry. It's a well-studied problem of numerical electrodynamics, and this problem has an approximate solution for any geometry of a radiator. Inverse problem, which is more interesting for practicing, is prediction of geometry from a set of required electrodynamic characteristics. The problem has not even approximate solution for the arbitrary geometry of the radiator. Today, the problem is solved by the brute force method, so usually the process of designing antenna requires a lot of time and a lot of processing power. Now, we present a machine learning based approach for fast design wire dipoles with difficult geometry arms. This slide shows information about our dataset. For three first Koch-type refractals, we changed central vertex coordinates, so for each refractal we had specified values for coordinate range. After that, we removed curves which have self-intersection geometry because dipoles for the curves cannot be produced. In the end, we had 640 samples for the first order, 335 samples for the second, and 307 samples for the third iteration. The figure shows central vertex coordinates for third order refractal. Let's consider the problem of prediction of optimal prefractal order by requiring an electrodynamic characteristic set. This is an important problem because prefractal order has a strong influence on the complexity of production. We used a decision tree algorithm whose main idea is building a tree with a condition in each node for the optimal splitting of a dataset. Therefore, we are trying to predict prefactor order by basic electrodynamic features, namely base frequency, bandwidth, and reflection coefficient. Therefore, with the classification problem with the unbalanced dataset, we use the weighted F-score as a quality metric. As a result, we achieved a 0.941 average F-score value on cross-validation. For the next task, we used a random forest method. Its implementation of bootstrap aggregation for a number n of decision trees as a basic algorithm. Each basic algorithm trained independently on a random subset. To obtain a prediction from the random forest model, prediction started on each basic algorithm and the result is averaged. The current task is the prediction of two coordinates of central vertex and arm length by basic electrodynamic features as a base frequency, bandwidth, reflection coefficient, resistance, and gain. We used mean absolute error as a quality metric on five-fold cross-validation. The table shows the mean absolute error for each electrodynamic feature. We compared result with a simple linear regression model and calculation improvement factor K. We concluded that more than a four-fold improvement in prediction quality was achieved for bandwidth, gain, and base frequency. For reflection coefficient S11 and resistance, more than a two-fold improvement was obtained. Additionally, we estimated the importance of features using permutation importance. The idea of permutation importance for the selected feature is the difference in the model quality estimated between the initial values of the chosen feature and the shuffle ons. We concluded that the largest contribution was made by the length of the dipole arm and the dipole height. In the end, we consider the reconstruction of the antenna geometry based on the electrodynamic characteristics discussed above: the base frequency, the bandwidth, the reflection coefficient, the resistance, and the gain. Let's build a model using the random forest algorithm to predict the coordinates of the central vertex and the length of the dipole arm. In the table, we display the mean absolute error for each predicted characteristic. For all iterations, the mean absolute error for the dipole length is less than 0.002. Coordinates of the central vertex have a 100 error. Thank you so much for your time. This slide displays contact information.
Any questions from the audience? I think author is present over here.
The presenter, one question I have that what kind of feature you have been selected for the random force?
Sir, I think he is not.
Presenter is here, please. Professor Patel, can you confirm that he is
I think he is not here.
available?
He is not available right now. Are you there?
Hello.
Author of 115.
Question
Yeah.
about how we calculate electrodynamic features.
No. What features you have used for random force?
Okay. I understand your question. For random forest we used next feature: base frequency of antenna, bandwidth, reflection coefficient, resistance, and gain coefficient. This feature was calculated by FICO program.
Okay.
Thank
So
you.
Can you just comment on that? You also have used the decision tree. What do you
Uh,
feel that which kind of ML technique more suitable for your proposal? Could you please comment on this?
yeah. Your question. Thank you for your question. As I understand, your question about why we used a decision tree algorithm. Yeah, it's true. It's correct.
Dr. Kumar?
Okay. We used decision tree algorithm for choosing optimal prefractal iteration because it's a task not difficult because we didn't use more complexity algorithms as random forest or gradient boosting. Um, we use for this task only decision tree, simple decision tree.
Dr. Kumar, are you there?
Yeah, please. Okay, thank you. Thanks for the addressing the concern. Please go ahead.
Any questions from the audience? I think there is no questions. So thank you very much, author
Thank you
of.
so much.
Okay. So author of 150, are you there? 150. Dr. Gadabe, author of paper ID 150. Dr. Kumar, he is not present over here and he has not given
Hello.
any. Yes, Dr. Kumar. So I
Okay,
think
so is the all the presentation has been done, or is there anyone is remaining? Please confirm that so that I
uh,
can.
all the presentation is over. You can give your
Okay,
comments
thank you.
or suggestions.
Okay, thank you.
If you want to
Okay,
give your suggestions or comments,
okay. What I will do, I will email you at the later stage.
okay, sir. Dr. Kumar, thank
Okay,
you very
thank
much
you. Thank you
for
for
sparing your valuable
providing
time.
me opportunity. I will be happy to serve in future as well. Thank you.
Okay,
Thank you.
thank you very much for sparing your valuable time for us and for this icSoftCom. Thank you very much, sir. Dr. Iyer, Dr. Iyer,
So, if no more presentation here. Yeah. Hello.
yes, sir. Now we are moving to the next technical session, that is S5. S4 is over.
Okay. So, may I leave or shall I stay
Yes, sir.
connected with
You can leave.
the
Yes,
session?
you can leave, sir.
Okay. Thank you. Thank you. Thanks for the invitation and your efforts for organizing the conference. I wish a grand success for it. Thank you.
Thank you, sir. Dr. Sailesh, are you there? Dr. Iyer? We are waiting for the session chair for the next technical session, that is the S5. Dr. Iyer? Okay, he is not here right now. So there are two papers in the next technical session, that is 186 and 209. So he's author of paper ID 186 present over here.
Yes, I'm here.
Okay.
But I've
So
sent you the pre-recorded video because my internet connection is unstable. So I would like, if it's possible, I would ask you to start it. Okay?
yes, yes, I'm starting that. Just a
Thank
minute.
you.
Dr. Ayyar, are you there? Silas Ayyar? Okay.
My name is Michał Pleby, and I will present paper CT MRI 3D fusion for cerebral system analysis. That work was done by cooperation of two institutions, Mikołaj Kopernikus University in Torun, Poland, and University of Warmia and Mazury, Olsztyn in Poland. At first, I would like to present the outline of the talk. First, I will present and discuss fusion scheme used in our system. Then I will present some remarks on registration, image matching. After that, I will present our segmentation approach, a few words about tubular reconstruction, error analysis, and semicircular plane definition used in our system, and I will show at the end some results. Our fusion system uses two datasets of the same patient, 3D volume MRI volume and 3D volume computed tomography volume. In case of 3D volume computed tomography, it's mainly used for bones and visualization of hard tissues, and MRI is used for soft tissues and vascular structures. In order to segment from both datasets vascular structures, we use volumetric registration to combine CT data and MRI data. After that, we perform three-dimensional segmentation from MRI data using the results of segmentation for boundary segmentation performed on CT volume. After that, we can create fusion of these data sets, extract segmented and reconstructed tubular structures from both data sets, compare them, and use them for further analysis. From mathematical point of view, matching process can be seen as an optimization process. We have to define optimization routine, in our case it's Pavlov's method. We have to define matching transformation. We are using in our system rigid body transformation, 6 degrees of freedom, and we have to define objective function. In our case, it's normalized mutual information. In our work, we are using combined method of segmentation of vascular structures. First, we are starting with MRI segmentation. We are starting from seed points because not always we want to extract all vascular structures. So we are starting with seed points. Around these seed points we are collecting intensities, building a probability model. So our growing procedure is checking if newly added voxels are consistent with previously added voxels. So if we segment this model and we are happy with it, we are using dilation to create a little pumped model, and we can use it for constraining CT segmentation. CT segmentation is a sometimes difficult process when we are adding a contrast agent to the vascular system. The intensities in a data set that are representing vascular structures are identical as bone structures. We have to remove bone structures. We can do it manually, or we can use a model from MRI data. This model from MRI data on the right side is used to constrain the left model on the left side, and we can remove these bone structures from our model. Tubular reconstruction method takes as an input 3D data. It applies filters, three-dimensional filters, to obtain segmented volumetric model into branches, and next step calculates and optimizes and smooths central lines, which are centers of final tubular objects. The last step optimizes the reconstructed tubular objects, generates joints, and improves shapes and geometry of final objects. This slide represents two tubular structures. Left one comes from MRI data. CT is represented in the middle. MRI data has two additional tubes because the vascular structures represented by those tubes they were not visible in CT data because they were immersed in bony structures. The right side image represents fusion, so we have superimposed these two left and middle models just to check if our registration is correct. In our work, we want to be sure that our tubular models are as similar as it's possible. So we have to measure distance between surfaces. We are doing it in two ways. First, a stage measures distance between tubular reconstruction and underlying segmentation, and the second stage compares two tubular models and calculates average Euclidean distance. As a result of our work, we obtained information that most of points of surfaces are closer than half a voxel size of original data. At this point, we can create our final model, which consists of bones reconstructed from CT data and vascular model from MRI. We can use this model for further analysis. Tubular structures can be described by many shape descriptors. Some of them utilize information about direction in space. This direction can be calculated by connecting both ends of such tubular structure with line. This line can be used for calculating directional angles. In our work, often the human head during an examination is slightly rotated. That can incorporate some errors during calculations of some directional information. Because of that reason, we wanted to introduce a new coordinate system, a semicircular coordinate system that is defined by 4 points, lower points of orbit margins, and semicircular canals. Using these 4 points, we can define a plane, and this plane is a base for our coordinate system. We can calculate two more planes, perpendicular planes to obtain for the final coordinate system. This slide represents a situation when we want to calculate directional angles of two A2 segments. The left image represents situation when we are working using default coordinate system, and the right one is calculated using our new stabilized semicircular coordinate system. In this work, we have prepared 18 fusion datasets. We have reconstructed left and right A2 segments for all datasets. We have compared directional angles for default coordinate system and semicircular coordinate system. We obtained some interesting results which showed that standard deviation for all angles has lowered, varying from almost 6 to 30%. We have observed higher correlation of orientation of A2 segments between datasets, and difference between left and right side angles also decreased. In this work, we have proposed method that enables CT and MRI volume fusion, tubular reconstructions, calculations of tubular segment descriptors, and we have also introduced semicircular coordinate system. Thank you very much, and I'm waiting for some questions.
Any questions from the audience? If you have questions, then you can unmute your microphone and you can ask. No questions? Thank you, Dr. Chalabias, Michael Chalabias. I think there is no questions from the audience. So we'll move to the next paper.
Okay, thank you.
Thank you very much. So next paper is 209, paper ID with 209. And I think Dr. Hers is there. Okay.
Yes, hello. Nice to meet you. Can you hear me?
Yes, I can hear you.
Perfect, perfect.
I'm
Also
playing.
with me is my co-author, Jim. Hello.
Hi. So I'm playing your pre-recorded video.
Yes, thank you. Hello and welcome.
Just a minute. I forgot one thing.
Hello and welcome to my presentation. My name is Benedikt Haus and I am one of the co-authors of the paper Soft Optimal Computing to Identify Surface Roughness in Manufacturing using a Gaussian and a Trigonometric Regressor. Together with my colleagues, I am working at the Leuphana University of Lüneburg in the north of Germany. It's located near Hamburg, and it's a relatively small university with 8,000 students. Nevertheless, we have a small but very intensely working engineering department. Okay, our paper ID is 209, so if you are interested, please feel free to check out our paper and ask questions if you are interested. Best way to contact us is by email, and you can find out our contact details in the paper. Okay, so in our project, we have the problem that we need to identify the roughness of a surface by means of the gloss that we can measure. Because the gloss of the first surface is one metric in order to evaluate the surface quality, which in manufacturing is an important problem. So in order to find a modeling relationship between the gloss and the roughness, we have employed the particle swarm optimization, which we use to obtain the parameters of a model fit. PSO is widely used in many non-convex optimization problems because we do not rely on a single particle to optimize our problem, but we have many, which can aid to find the global maximum as opposed to only a local maximum. However, it's always a balance to find between exploration and exploitation of the convergence phase. And there's almost an optimal dimension of the search space with respect to accuracy and time convergence. So in conventional particle swarm optimization, the particles are guided by three components, the first of which is the present movement, which is also called the inertia component. And the second one is the personal experience of the particle, which is typically called the personal best or p-best. And the third one is the social component, which is called the global best, or the overall best of the swarm. Here's some nomenclature, which is also pretty standard. We consider our particles with capital X, boldface, and our velocities, which describe the change in position with capital V. Okay, so the basic PSO structure, which I'm sure all of you know much better than me, is given by these two equations, where we have K1 and K2, which weigh the personal best and global best components, respectively. The personal best component in literature is also often called the cognitive or individual or exploration component, while the global best component is usually called team best or social component or also exploitation component, because it is a component that signifies the group intelligence of the swarm. And in the matrix X, we are storing the individual particles and each parameter in the columns. The main contribution of our paper is to extend the search space, depending on the number of parameters to be found, in order to make the algorithm more accurate, so find better optima, and also make it faster. Okay, so our approach is to utilize not only the global best component, but also the second best and third best components, which we indicate by 2gbest and 3gbest and so on. And as you can see, we have augmented the first equation, which was the velocity upgrade equation, and the new equations are given here as 3 and 4. And if we want to make the search space as large as the parameter space, we can use a maximum number of d minus 3 terms for gbest, where d is the number of parameters to be found. Okay, and the main idea is to increase this search space and get its size nearer to the d-dimensional size of the parameter space, because if we increase the volume of the search space, then the density, so to speak, of the particles in such a given space decreases. So in order to get good results using this approach, it turns out we had to increase the number of particles of our swarm. Nevertheless, we get more accurate results in faster time, even though we had to increase the number of particles. Okay, here we can see our regressor, which consists of an exponential component and also trigonometric components, and the parameters 1 to 7 are to be calculated. Okay, so here you can see a flowchart. Maybe this is a little bit small to see in the video, but we have also uploaded the slides for your convenience. And the algorithm is based on conventional PSO, but additionally evaluates the second best and third best components of gbest. Okay, we also did some experiments using real measured data. We did them on a Core i7 6700, so it's a relatively old CPU. Also, it's being slowed down by the fixes for Spectre and so on, or the CPU security vulnerabilities. So with modern hardware, it probably is already a little faster. So the variants that we have compared are the conventional PSO algorithm without any global west components. So by setting K2 to K4 to 0, we achieve what we have called anarchy in our context, just a little analogy. And the conventional PSO variant we have called PSO one chief because there is one global best component. And then there's a variant involving two chiefs, which we achieve, which we enable by setting K2 and K3 to something that's not 0. And there's also three chiefs where we use the best global best component, second best component, and third best component. And as you can see from the figures that I'm about to show you, we have the fastest convergence using the variant with two chiefs, so with two global best components. But we have the best SSE value, so some squares of errors, if we use not PSO but genetic algorithm, which we have implemented in order to have a comparison baseline. However, it turns out our PSO variants, all of them, are much faster than the genetic algorithm. So we have also computed an efficiency index, which consists of time and SSE accuracy. And in terms of this efficiency index, the PSO variant with two chiefs by far is the best variant, also in terms of time. Okay, here is some figures for you to look at. As you can see, the time is the fastest if we use this variant. And also the SSE is relatively small. It's not as good as the genetic algorithm, but it's much faster. Okay, here we have our pseudocode of the algorithm. First, we initialize the positions and the velocities randomly within given bounds. And then we check if we are already at our goal by comparing against the tolerance. And then, if we are not already at our goal, we initiate the main loop of the particle swarm optimization, which you can see here. And as you can see, the main difference is that we update G2 best and G3 best and use it in the next loop of the calculation. Okay, that concludes my brief presentation. I hope that you have found it interesting. And if there are any questions, I'm happy to answer them after this video presentation. Thank you for your attention.
Any questions from the audience? Anybody? Okay, Dr. Benedict, I just have one thing to ask you that you use the PSO for optimization and you have compared your results with the genetic algorithm. But have you compared your algorithm, extended algorithm for the other kind of optimization algorithm, like is ant colony optimization or other?
No, so far we have not compared the optimization with this specific data set with another algorithm because we have relatively sparse data and we have 7 parameters to optimize. So algorithms that are less stochastically based, unlike PSO and genetic algorithms, turned out not to yield sensible results. So only algorithms with a random component, like genetic algorithms and PSOs, were able, with this data set at least, to give us a set of parameters that fits our regressor relatively well. So in this case, it seems the problem is relatively non-convex, and yeah, for this reason, it seems it is advantageous to have random components in the algorithm. But we have not tried any others, no. Thank you for the question.
Okay, no problem. Anybody else? If you have any questions,
Sir, I have one question. Sir, what is the need of this more extended surface extensions?
Excuse me, I didn't really understand the question.
Search extension. What is the need of these search extensions?
By the extension, we mean the extension of the search space. If we consider the update equation of the PSO, we have several components, the inertia component and personal best component and global best component. And you could consider this as three vectors in geometric interpretation. And we can extend this summation using more vectors. And in this way, span a larger room, a larger area,
space, yeah, space,
a larger space.
yeah,
yeah, exactly. So yeah, this is our approach basically. Excuse me, I didn't. I'm not sure if I understood the question correctly.
Okay, thank you, sir.
any other questions? Okay, so there is no questions. So Dr. Haas, thank you very much for presenting your and answering the questions. Thank you very much.
Thank you.
Okay, so this end of this technical session as 5, and this also end of the first day of this icSoftComp. So I am really very thankful to all the audience, all the attendees, those who are right now present in this meeting. Thank you very much for your presence in this icSoftComp. We will see you tomorrow in the morning at 10 o'clock. Thank you very much. Bye, everyone.